So let's first talk about, our constraints here, which in this case are what are the weaknesses of zombies. First off, zombies can only travel by land. They are too dumb to figure out how to fly. They can be taken in axe to the neck, also bullet to the head. But they're also not dumb, as they do eat brains for a living, and they also know not to mess with Texas because they got this guy here. I'm protecting them. So, here's our problem. The zombies have taken over. They have invaded. But as we know, Texas lives on. So we're going to set up our point of operations at Rackspace in Dallas, as the only survivors. So assuming that we can still get internet here, so we're assuming that the zombies are not smart enough to cut the oceanic internet pipelines, we have to figure out how to keep Zombie Book running when the entire country has been taken over by zombies. Sound hard? No? Maybe? Okay. So let's first talk about what are the components of this web application Zombie Book that we need to keep up. So as with any web application, you have a web server, you have an application, it could be Rails, could be Django, could be anything you want, Java, .NET. You're going to have a set of APIs that it actually talks to. You're going to have a database. You're going to have a caching layer, most likely, if your website you want to be responsive. You're going to have an operating system, and you're going to have a hosting provider that you use. But you need it to be zombie-proofed. So the parts of the application we are going to be talking about that actually need to be zombie-proofed are your host, your application, your database, your cache, any third-party services that you choose to use, and whatever process you choose to use to serve your application. Okay, so today, Zombie Book exists. But we didn't realize when we first made Zombie Book that we actually would have to survive a zombie invasion. It was an MVP, it was a proof of concept. So for our host, we used Heroku. We're sitting in Amazon, in the Northeast. It's single data center, single availability zone. Our application is a Ruby on Rails app. Our database, we chose to use Postgres. For Mem Cache and Redis, we use a third-party service. So it's a hosted by someone else, Redis and Mem Cache service. We also chose to use a bunch of third-party services. SendGrid, New Relic, ClearDB, WebSolar, Iron.io. Probably in your applications, you are also using a wide variety of third-party services. Does anyone not use any third-party services? No one? Yeah, thought so. And that's just the nature of building apps. We like to save time. We don't want to rebuild the wheel. There's certain things that are better off doing it that way. But that's Zombie Book, and it looks a little something like this. So we're sitting inside of Virginia. We're running MySQL there, or Postgres, or whatever you want. And then for all these third-party services, you need to go out to the internet. Those third-party services might be hosted in Google, Rackspace, AWS. You don't know where. You don't care. They're just out in the internet somewhere. And that's normally okay. Before the zombies, that was fine. But it might not always be what we need. So we'll start with the host. So the hosting requirements when you need to survive zombies. Your requirements are, you need to be on multiple continents in multiple data centers. Because if the US goes down and all of North America goes down, we still need to be hosted somewhere. And we need to be in multiple data centers when we do it. Of those data centers, they also need to be completely isolated. So if, let's say that, a certain company, let's call it Amazon, perhaps they shared some code between their European and North American data centers, and the zombies, one of them got a little smart, and he decided to hack into the Amazon infrastructure and took down both sides. Now we're down. which is why you need to be on more than one hosting provider. We also need to be infinitely scalable, because we don't know when we're going to repopulate, but when we do, we want to be prepared, which is why we need to be in the cloud, because obviously the cloud's the only infinitely scalable place there is. And we should be on 2 different hosts, as I said. These are some examples of what those could be. And they have to be independent hosts. So if just using 2 different hosts that sit on Amazon doesn't count, they need to be in 2 different data centers, physically separated. Okay, so the actual application itself. You need to program your application so that it's server agnostic. Nowadays with 12-factor apps and things like that, that's become less relevant, but we need to make sure that we're not dependent on any one single server, which means you need to have no local files. If any file is uploaded, it should be on S3. It's beside the core files that are sitting in your Git repo. They should all be hosted somewhere else so all the servers can pull from it. We're also assuming in this case S3 wouldn't go down, but go figure. So no local caching. This means that if you have a bunch of servers, if you want performance when you're running in multiple data centers, you can't do local caching on each individual server. The reason for this: one server goes down, and then you bring a different server back up. For every performance, for every call to that server until it's back up to date with the cache, those calls are going to be very slow, assuming you're making good use of your cache, which you should. So you need to make sure that you're using a separate cache. So in Mem Cache, you have a separate Mem Cache, server. So in our case, a Couchbase server or a Couchbase cluster somewhere else that's actually handling your cache for you. And your application also needs to understand how to deal with replication lag. So with any database that is running in multiple data centers, your application needs to understand that it might not always have the most up-to-date data when it makes a call. What does that mean? That means I add something to my database, and then I immediately try to retrieve it. When I'm retrieving it, I should be reading from a slave, because whatever I'm doing is most likely clustered. So when I make that read, my application needs to know that it might not have the most recent data. So you either need to put it in a cache so that you can pull it, or if you're inserting an object, keep a copy of that object for use. So the actual database that you choose to use. Now, it needs to do something like this. Now, with Couchbase, you've heard about the cross-data center replication a few times, but that's essentially what it's doing. Let's say we have 2 clusters, wouldn't be across the US in this case, but that's a graphic I pulled offline. And you have 2 separate clusters that are asynchronously replicating between each other. And the reason why it has to be async is that if it was synchronous, that would mean that when you did a write to data center 1, it would have to go talk to data center 2, make sure that it's committed to that master, and then when it comes back, it would return to you. Now, given the speed of light, that's going to make any query you make, any insert, it's going to be very, very slow. So that's why it has to be async, and you have to find a way to solve the inevitable problems you have when you're writing to 2 different data clusters. So your options for a database in this case are limited. There's only a certain number of actual applications that can do this. So let's say you were using MySQL. If you need SQL to do this, you need to use something like a Continuate, which is a replication software. Basically, it uses native MySQL. It'll sit on your database server. It's going to read from the bin log, and it's going to send the bin log over to the server that it's writing to. And it provides an easy-to-use interface to do that. GenieDB doesn't use a clustered setup. They do. It's all masters. Basically, a ring of masters. You can have as little as 2, and it's just it's basically they rewrote InnoDB, so it's not fully MySQL compatible. But it does accomplish what you would want if you wanted to be in multiple data centers, but didn't have a need for slaves. If you're using something like Postgres, there are solutions out there for you, ish. None of them are particularly good, and someone really needs to write a continuous function version for Postgres, but currently nothing is easy. Most people who choose to use Postgres and go across data centers, they end up writing something custom. But if you know of an option, let me know. NoSQL options, CouchDB is really the only one that does this really well. Mongo, not a great option here. They don't provide, you can do it, you just can't really do it well. In my experience of trying to do it a few times. Things might have changed, but CouchDB and Couchbase provide a great solution for this. As you know, with Couchbase, there's an interface, like it's point and click. Like you can be in multiple data centers with your database in literally like 5 minutes. It's kind of dead simple. But at the end of the day, this is what you're trying to do. You're trying to have one database in one place and one database cluster in another place and have them send data between each other. Next, your cache. Can't forget your cache. So there's a few requirements of what your cache needs to be able to do. It needs to be replicated, and it needs to be on multiple nodes. Caches go down, and so it needs to be on more than one node. And there's really only 2 solutions that can actually do this. The first being Redis, using something called Redis Sentinel. It's not point and click. It requires a good amount of knowledge of how Redis works to actually get it configured. Redis Sentinel is not considered production ready. I believe it's an alpha release at this point, but they do allow you to at least set up multiple nodes. Most people are not using that in multiple data centers though, except for pointing it out to like an analytics or something like that, or another data center to pull that data out. And then the other one obviously is Couchbase. You obviously get a Mem Cache Api. It's very easy to use that you can just act like it's a normal cache. So then you actually need to serve this application up. And it needs to be repeatable. So if you've been at any conference or been reading the news lately, there's a little thing called Docker. They're kind of a big deal. And they make this really easy. If you're going to be sitting on multiple hosts and multiple providers, you really need to make sure that whatever you're doing is repeatable and works the same way on every single host. A large problem people often have is you go into multiple data centers and you end up writing custom code for each center because there's a different version of the operating system. So you install a different set of packages, and then things stop being repeatable. So you need to make sure that it's exactly the same, and that's what Docker can guarantee for you. A Docker server looks something like this. So the inside is the web. Those are front-end servers. Rescue, that's a name of a Ruby queuing system, and they sit in the middle. You're going to have several different instances of each of those. You're going to have Docker running each of those, so you're actually going to have 8 different Docker instances basically running. And then on that server, you would throw something like Nginx or HA proxy in front of it to actually route your traffic between the front-facing web ones. You obviously wouldn't point those towards a background process. But this makes it repeatable. So it's always going to run the same version of Ubuntu. It's going to run the same version of Docker, the same version of all of these. They actually make it hard for you to log in and make changes, which is good because you don't want to. Instead, you have something that looks something like this, this is an example of a Docker file. Basically, if you're familiar with Bash, a Docker file is pretty simple. It's basically a list of commands that are run when you do basically like Docker build. or Docker make, and it's going to create this image for you out of this Docker file. If you're familiar with how a make file works, basically the same, just a lot simpler, because they're just a bunch of commands that you might have run anyways when you're configuring a new server. Pretty straightforward.